and we just start with Polish space W, just space of. It's best to think of it as space of realizations of some stationary process or random field, but for the moment it's just Polish space. And in this Polish space I have some subset V. This is such situation also often arises. For example, I take those of my random variables which have exponential moment less than 1 or something like this. And I have a map. Which I denote G. So from eta times V into W, where eta is a subset in the space of measures on W, in the space of probability measures on W. So just the point, so let me give a very simple example. So if I have stationary, not stationary, just any stochastic process, then it is possible to consider its normalized exponent. Just something like this. This is a very important object because it is possible to extend this definition not just to exponents of processes, but also to exponents of some fields. So even if this process converges, this stochastic process converges to some generalized stochastic process defined usually on appropriate Sobolev space, then the exponential converges to a random measure. This is theory of Mandelbrot, Perrier, and Kahan, developed, by the way, starting from problems in Kolmogorov's theory of turbulence. And the idea of Mandelbrot is that this exponential models, in fact, dissipation of energy in turbulent flow. Okay, but in any event, so let us observe that this map here, the transformation depends itself on the measure. So this is why I take this transformation, which transforms space of measures times, well, my phase space into phase space itself, something like this. Okay. So this map induces a map on measures themselves. So if I have a measure eta in eta, then I can define G star eta is precisely the push forward of G. And push forward of G eta of the map parameterized at eta, push forward at eta. So the measure is pushed forward by this formula. And once I consider this transformation, so the key result, the key proposition that I present today is the following, that just this correspondence G to G star is in fact uniformly continuous. But I have formulated the conclusion, but I have not yet formulated all the assumptions. There are some assumptions come into play, which I will now formulate. Is uniformly continuous. So I need some additional assumptions. In fact, first, before even speaking about uniform continuity, I need to give topology on the space of maps G and on the space of maps G star. So it's easier on G star. G star is just a map, in fact. So by definition, G star is a map from eta to the space of measures on W, and this is endowed with Chebyshev topology with uniform topology. So this is not a problem. One needs to choose a metric on the space of measures, and for me it's convenient to choose the Levy-Prokhorov metric. Let us recall that measures are epsilon close in Levy-Prokhorov metric if measure of, so there are two measures, measure number one, measure number two, and they're epsilon close if the first measure of some set is less than the second measure of epsilon neighborhood of this set plus epsilon. This is very convenient, very flexible definition introduced by Prokhorov, and in fact who was basing his work on the previous work of Levy, and this is a very, very, very useful definition. Just measure of a set is less than measure of epsilon neighborhood plus epsilon. This definition gives very good flexibility, just very useful for our purposes, but in fact it metrizes the weak topology on the space of measures. Okay, so now for this I need to introduce distance on such maps. This is a little bit trickier, and in fact the distance I introduce is the following. So distance between G1 and G2 is introduced by the following. So I consider the measure of the set. Let me introduce some additional notation. I consider the measure of the set eta, measure of the set G1 eta t. I'm in a metric space, so G1 eta t distance between G2 eta t is less than something, let's say 2 to the minus k, something like this. So I consider the measure of this set, the measure eta of this set, and now I consider supremum in eta. This is the key point, supremum in eta of this. And this I denote dk, let's say, dk. And then of course the distance is as usual. So with these quantities, the distance is as usual sum 2 to the minus k dk over 1 plus dk, something like this. The key point here is that I take this supremum. This is important, so that just maps converge, one map converges to the other map if the image converges to the other image uniformly over all eta. Uniformly over all eta. This is the key point for me. So this is a set, by the way, I didn't write it very clearly, but let me write it very formally. This, of course, is the set of T. The set of T in V. The set of T in V is supreme eta of the set of T in V. With this quantity, the distance is bigger than 2 to the minus k. Okay, so yes, so this is just a metric of uniform convergence, uniform in eta, uniform convergence in probability. Uniform in eta, convergence in probability. Okay, and now I need to make one more requirement, which makes the whole result work. So the requirement is the following. I consider, I think I said it, but let me write it, that eta is a compact set. But also it is important for me that the image of eta be contained in some fixed compact set. The image of eta must be contained in some fixed compact set. So with this key requirement, so let me make this requirement 1. Let's write requirement A. So under requirement A, let me emphasize this. Under requirement A, this map is uniformly continuous. This map is uniformly continuous. And in fact, the proof is not particularly difficult. One first reduces using, in fact, compactness and using Stone-Weierstrass theorem. One reduces, well, the Stone-Weierstrass theorem, one reduces to the case when W is C to the N, and when it is C to the N, in fact, convergence of finite dimensional distributions implies weak convergence, and convergence of finite dimensional distributions is precisely what is guaranteed by this assumption. So the key point, where is our chairman? Yes, how much time do I have?
15 minutes.
15 minutes, okay. So then I can explain in detail. So the key point here is just not the result as such, but the applications of this result. And now maybe let me try to maybe this. Okay, very nice. Okay, so now we turn the page, and this is advantage of these marker boards. It's very convenient to turn the page. And we go to specific application, and in fact, let me consider a very specific case, even though the results can be formulated in greater generality. Let me just consider one very particular case just for concreteness. So I start with the Sobolev space h dot minus 1/2 on the circle, which is just the completion of smooth functions with respect to the following inner product. Inner product of f1 and f2 is the integral, the double integral. f1, let me write at this moment in additive notation, e to the theta 1, f2 e to the theta 2 times logarithm of what? Of distance e to the minus theta 1 minus e to the theta 2. And of course, this logarithm has to be positive, so of distance to the minus 1 or minus logarithm. So d theta 1, d theta 1, d theta 1, d theta 2. So this is my Sobolev space. So what is this Sobolev space? It is more convenient to think in terms of maybe more usual, more frequently met Sobolev space h dot 1/2, h dot 1/2, when the norm f1, f2, the inner product. Let me just write for h dot 1/2. Let me just write the norm. It will be easier. The formula will look nicer. But of course, one can also write the inner product. It's just a bit messier. Ff is just the integral f e to the I theta 1 minus f e to the I theta 2 e to the I theta 1 minus e to the I theta 2 squared d theta 1 d theta 2 over. Right? So this is just the usual Sobolev 1/2 space. Please observe that I do not add here the term corresponding to L2 norm. It's not very important on the circle, but it is important on, in fact, on the real line. One can, of course, consider analogs of this on the real line. So, and this is the antiderivative of this space. This space is the antiderivative of this space. Okay, so if a function belongs to this space, then its derivative belongs to this space. This is the idea. So, okay, so, and then I consider Gaussian process corresponding to this space. So I consider to each function f, I assign Gaussian random variable with the same vectors. Yes, sure.
They integrated our segments.
Over the whole circle.
Circle.
It's circle.
Yes, I see. But the function defines our exponent of the page. Theta. What runs?
Excuse me.
I don't understand. G.
Theta 1 is from minus pi to pi. Yes.
Yes, but integrated, but see, and then segment.
Yes.
Мы интегрировать должны на это есть. А вот интеграл So that you have
So T's R over 2 pi z?
yes,
It's in additive notation.
yes, but
It's an additive notation. Yes, it's correct.
this one.
Is it okay? Is it okay? Okay, so just the usual. It's convenient for me to use just the additive notation for the circle. Okay, is it clear? Yeah. Okay, good. We have this. We have this space, and to each f I assign just Gaussian random variable with the same variance. So okay, then it is in fact useful to consider these Gaussian random variables not in the circle but in the disk. And in fact, you are right. Here there is implicit exponential map. This is correct. In the circle, not in the circle, but in the disk. And then, in fact, if I consider my stochastic field on smaller circles in the disk, so I have just Poisson kernel that integrates the field, and Poisson kernel, of course, belongs to the space. So I have then stochastic process xr of theta, theta again in additive notation. Of course, one has to be careful keeping track of this. Xr of theta, where r is the radius of this circle. And then it is possible to prove, so what is xr of theta? It is just a random field applied to Poisson kernel at r theta. This is what it is. Poisson kernel at the point r theta. So the Poisson kernel converges as the radius goes to 1, the Poisson kernel converges to delta measure, and so on the boundary of the circle I don't have stochastic process, I only have stochastic field. But the exponential of this quantity, and let me write it like this, in this Gaussian normalization. So this exponential, in fact, does converge to a limiting measure. Gaussian does converge. So this is the result of Kahan. If r goes to 1, yes, and in fact, it's important also to keep track of what is gamma. Gamma, in fact, in this example, has to be from 0 to 2. Okay, so now the key point is that I would like to apply this theorem of Kahan. Let us look at this, and maybe let me erase the definitions of Sobolev spaces. I would like to apply definition of Kahan to non-Gaussian case, and in fact I have. So now I will be not on the circle, but on the real line. All the definitions are the same. And in fact, a real line, one can consider a real line as just Kelly transform image of the unit circle. And I consider a random field which is non-Gaussian, where exponential of x of some phi, there is Gaussian term. But there is also non-Gaussian term, and I consider a very specific model where the non-Gaussian term comes from, in fact, from the second theorem of Séguin. And it is a term which is, in fact, a Hankel determinant. It's determinant of Hankel operator. In fact, it's a very specific Hankel operator. Here I'm on the line. Here I'm on the line. The tilde means inversion in Fourier space, as always. And just the Hankel operator, the function h, so I write phi equals to phi plus plus phi minus, where phi plus is the decomposition onto positive frequencies and phi minus decomposition onto negative frequencies. And h is the exponential of phi minus minus phi plus. So it is essentially the exponential of the Hilbert transform of my function phi. So, and this is a formula. These fields of this type, they arise in study of random matrices. Study of random matrices, in particular of random matrices with unitary entries. Please allow me to skip the details. But the point is that there is this non-Gaussian term. And in fact, even for this non-Gaussian field, it is possible to prove convergence to Gaussian multiplicative chaos, convergence in distribution to Gaussian multiplicative chaos. And in fact, the key role in the argument is played precisely by this uniform continuity theorem, because the statement on exponential moments is precisely convenient for checking such conditions, and in fact the compact set eta tilde is precisely the compact set where random variables have their exponential moments uniformly bounded, and such set is compact. Thank you very much.